Hello again, and welcome to the next unit in our Design For course. In this session, I'm going to be sharing my brief history of manufacturing, which is a quick dash through the way manufacturing industry has evolved over the last couple of centuries. We'll focus particularly on topics such as design for manufacture, design for assembly, and more recently, design for test, service, environment, and so on. In our next virtual classroom session, we'll dive into each of those themes in a little bit more detail, with following sessions going further still into some of the main topics. In the earlier sessions, we've covered some core principles that underpin all aspects of product lifecycle management, and now we're going to dive deeper. Hopefully you'll remember that I outlined in earlier sessions the key streams of time to market for product development and time to customer for product supply, showing where the various product lifecycle courses fit in. Now we're going to focus on the way that the requirements for later in a product's life, considering both its production and its use, might influence the design and the design process. Traditionally, this course has been designed for manufacturability, focusing primarily on manufacture and assembly. However, it's become increasingly clear in the last few years that the other aspects deserve more attention, hence the move to design for X, where X can be many different dimensions of design requirements, covering how the product is supported in the marketplace, how it's marketed, what happens at the end of life of the individual item or when the product is no longer produced, and so on. So, to give you a view of what's coming up over the rest of the course. In our next virtual classroom, we'll explore the main ideas about designing for this range of other considerations, how the various considerations might cause some tensions one to another, how we resolve these, and then how we develop process and guidelines to make sure we put those ideas into practice. Following that session, I'll invite you to think about what the design challenges might be in your organisation as you start to apply these principles. In subsequent sessions, we'll dig into the various aspects in more detail. On this course, we will look at design for manufacture, the process of making parts, and design for assembly, the process of putting parts together. And all these units make up the design for manufacturability course. In future, we'll be developing modules to cover other aspects, initially service and sourcing, that you'll be able to come back and do at a later date. In this video session, I'm going to give you my take on the evolution of manufacturing, manufacturability, and some of the other themes that have come to the fore in recent years, and add additional dimensions to take into consideration during the design process, particularly Industry 4.0, servitization, and yes, that really is a word, and the needs of the circular economy. As you work through the video, there are some questions that I'd like you to bear in mind. You should have downloaded this worksheet with the questions and space for your notes. So if you haven't done that, maybe pause the video at this point and find that before you move on. So off we go with my brief history of manufacturing. You'll remember I used this illustration to show the evolution of industry over the last couple of centuries. When I was younger, people used to refer to the Industrial Revolution, referring to the period in the late 18th and early 19th centuries when machines started to replace hand production methods. There were new production processes for chemicals, iron and so on, and increasing use of water, steam and later coal power. It's only more recently, with the idea of Industry 4.0, that these four distinct phases referred to as Industry 1.0 to 4.0 have come into common use. While industries developed as a continuous process, today we recognise these four distinct transitions in the evolution of industry, and they form a helpful framework for the theme of this session, touching on some of the milestones in that evolution. So let's start with what I knew as the Industrial Revolution, now referred to as the First Industrial Revolution or Industry 1.0. Before the Industrial Revolution, production was by highly skilled craftsmen working in small businesses. Mechanisation drove change both in the way products were made and the way firms were managed. Even in the early days of the automotive industry, craftsmen would make an individual early car by fitting together a set of uniquely manufactured parts. It may seem incredible now, but it was revolutionary when parts could be made to a sufficiently consistent standard that any one could be replaced on an assembly without lots of fitting and fettling. This development allowed Henry Ford to mass produce cars in Detroit at a scale never before previously attempted. And he didn't need to train craftsmen. Most jobs in the factory were so specialised and simple that they could be taught to immigrants straight off their ships, organised in gangs speaking the same language. Ford's approach led us to the second industrial revolution, the era of mass production. As Ford's ideas developed, he came up with the idea of the moving flow line. Originally, cars were built in one spot and the workers moved from one car to another. Initially, the moving flow line was no more than a rope attached to a big winch that pulled the cars along. So that meant the cars moved, the workers kept stationary, and that enabled even further improvements in efficiency and a reduction in cost. At its peak, up to 10,000 cars a day rolled off Model T production lines around the globe, and as volumes rose, prices came down and made cars more and more affordable to anyone due to the economies of scale that resulted. Part of Ford's success was recognising the need to design for ease of manufacture, which some would refer to as producibility or manufacturability. And so we can see that the history of design for manufacturability is connected to the history of manufacturing itself. Back in the day, engineering students would used to take shop floor courses to get familiar with manufacturing process and to avoid adding unnecessarily to manufacturing costs during design. However, as things evolved over the following decades, other stuff started to get in the way. Ford's approach to manufacturing was based on the belief that economies of scale provided efficiency and lower cost. And while he produced lots of cars all the same, that was probably true. Production was characterised by large batches of components being made on machines for maximum efficiency. We might have grouped lots of similar technologies, so a shop full of lathes, grinding machines or whatever, so that again efficient production could be organised within one technology. In those days there was a long changeover time between one operation and another, therefore changing machines to produce different products actually consumed a lot of time, which is what drove the idea of large batches. And as I say, as long as everybody was buying cars the same, the cost effect of that was relatively small and the economy of scale was valuable. However, as time progressed, consumers started to want more and more variety in their cars. You'll remember the famous adage, any colour you like as long as it's black. But as soon as we wanted different colours, different engines, different body styles, extra accessories added, life got more and more complicated. And as planners tried to wrestle with that, we were getting complicated forecasts. We still had big batches, which meant there was lots of inventory because the actual requirement for individual parts over time was becoming smaller as people wanted more variety. As computers came along later on, that meant we started to have an information factory to handle variety because the volume of paper just got too hard to handle. Alongside that, because we were producing in batches, if there were any defects, they didn't always get found early, and we were relying on these being inspected out later in the process. Because of the need to do batches and changeovers, the end-to-end process time got longer and longer. You know, we forget that in the early days of Ford, he could take raw iron ore in at one end that would have become a car within 48 hours. And that 48 hours got longer and longer and longer. Attention within the operations was really about local efficiency, not looking at the optimization of the whole end-to-end process. and management increasingly became around numbers and budgets. Of course, that approach has the downside of lacking flexibility. It's tying up cash, it's tying up space, it's adding time, and also we get significant consequences of quality failure because quality defects are often detected late in the process where there is potentially a huge inventory of defective product to be dealt with. So not great. Another downside of this increasing level of complexity was the need for a lot of difficult planning, and getting the most out of every worker led to the creation of specialised industrial engineering roles, the stereotypical men in the white coats with clipboards and stopwatches. The attitude towards workers was don't think, just do, which inevitably led to motivational issues, subsequently bringing in piecework and bonus systems in a drive to get workers more and more motivated. But one of the characteristics was decision making and work were increasingly separated. We introduced lots of inspection regimes to make sure we got the quality, which, as you can imagine, had further demotivating effects. So there was a huge loss of morale and pride in the work, leading to high absenteeism and staff turnover. Now, by that time, Ford was an incredibly profitable business. So Ford's answer initially was just to raise the workers' pay. He was astounding others in the industry at the time by offering them $5 a day, which was more than double the rate that was being paid by other organisations. But that simply had the consequence that board workers became rich board workers. And if you just want a bit of a laugh and a sense of what that time was like, there's a lovely Charlie Chaplin film called Modern Times. Full movie might be a bit much, so you can just watch the factory scene if you like to see what I mean, and I've provided the links for you here. While cars evolved a lot in the next 30 to 40 years, actually not much happened in the terms of how they were produced, and as the size of organisations grew, the connections between product design and manufacturing eroded. As costs rose and profits fell, attention turned again to the study of design for manufacture. The 1960s focus on ease of manufacture resulted in people assuming that several simple shaped parts are inherently less expensive and simpler to manufacture than a single complex part. Savings from making parts simpler were believed to more than offset any assembly cost increase. The manufacturability guideline example shown here recommended choosing simple parts that would be right over a very complex multiple bent part which would be wrong. The complex part was assumed to have more waste material, and actually two simple parts could be cut out of strip material, bent all in one direction, and it was simply a case of putting those two parts together with a bolt. Obviously looked cheaper. However, when you do the maths, it actually doesn't come out that way. We discover that even ignoring assembly costs, the two parts in the so-called right design are significantly more expensive when you add the costs together than the single part in the wrong design. So even the piece part costs, neglecting tooling, are more expensive. For sure the tooling's cheaper, but that doesn't help us. And by the time we've added assembly cost on as well, there's a significant difference. So we can see that it's not always obvious which design is better when we look at total cost of manufacture. It became increasingly clear as we sort of moved through the 60s that it wasn't all about the manufacturing process of the parts, and all the other costs associated with the parts that were on the table in the previous slide, so things like setup cost, processing cost, material cost, tooling cost, and all the other things that haven't been listed that are associated with parts before they turn into a product, like procurement, receiving, inspection, storage, all start to add up. I mean, if we take something simple like fasteners, they're only about 5% or so of the bill of material cost in typical products. but they can account for 75% of the labour cost, and they all have to be managed through the supply process. And that led to a line of thinking that said a reduction in the number of separate component parts generally reduces the cost of assembly, but also the total cost of the parts. Now, of course, that could be taken to extreme, but that was a great place to go. This became increasingly true in the 1970s, where the focus started to be on automation and the introduction of robots. Now, of course, the early robots were relatively simple things and didn't have the dexterity of human arms and fingers in the way that perhaps some of today's modern robots would have. So a lot of interest led to understanding what kind of parts can be easily fed and oriented automatically, or which are going to be difficult or even impossible. So solutions were sought that made life easier and easier for the robots. Research in this period focused on developing rules that product designers could use to avoid shapes that were difficult to feed and orient, and provide features that facilitating that process, and particularly around quantifying how we would design for ease of assembly. Here are a couple of examples. If we take the first example, it's very clear that a robot arm is going to have a lot of difficulty getting that first bolt located, the one on the left hand side, and design changes are required to make locating that bolt easier. Human fingers might be able to do it, but a robot definitely couldn't. Similarly, something that was completely round, would be very hard for a robot to pick it up and know that it was correctly oriented. So things like flats needed to be put on to make sure that the robot would hold the part in the right position. Now, of course, if you stop and think about that for a minute, what's true for a robot is probably also true for humans. The more we introduce those features, the easier their job would be, and therefore the labour cost would have come down anyway, robots or no robots. In parallel with these developments in manufacturing methods and the study of design for manufacture and design for assembly, developments in the market continued. With more and more brands available from around the world, customers were increasingly looking at products more suited to their needs. And we entered what is now referred to as the era of mass customization. High volume products increasingly tailored to customer requirements. And yet at the same time, people were looking more and more for competitive costing, and prices were being driven down. So those two things were working very much in tension with one another, and increasingly manufacturing companies were looked at ways of optimizing their design against the costs, particularly in the face of increasing competition from the Far East, particularly in the 70s and early 80s from Japan. Before we move on and look what happened later in the 80s, the 90s and the early years of the 20th century, it's worth just pressing pause on that for a minute and rewinding to look at what had been happening in Japan over the same sort of time scale. I want to go back to the early years of the 20th century, to the villages of Japan and a guy called Tsukichi Toyoda. And Toyoda's family were all weavers. They worked to produce cloth out in the villages. And young Toyoda would look at the work that his mum and his grandmum and his cousins and aunts and so on were doing, and think of ways to make it simpler. So he went into designing and manufacturing looms. And one of the things he noticed was the amount of time wasted when the thread broke in the loom, because it wasn't always noticed because of the speed at which the looms worked. And once it was noticed, there was often an awful lot of deflective cloth that had to be thrown away. So Toyoda came up with the idea that if he could invent a loom where the machine stopped when the thread broke, that would attract attention and the problem could be solved without producing a lot of defective cloth. Now, this loom was very successful and came to the attention of the weaving industry in the UK, and eventually Toyoda sold the rights to the design of his automated stopping loom to a company called Mather & Platt, who were based in Yorkshire, for quite a bit of money. And he used that money to fund himself and his son Eiji to start a car making business, which was the forerunner of the Toyota car manufacturing company that we know today. The fledgling Toyota car industry was set up in the 1930s, and it was a small player in a world dominated by the US and European automotive industry. Toyota and his colleague Taiichi Ohno visited the US in the 1930s and were really impressed by what Ford had done and learned a lot from him, taking those lessons back to Japan. However, when it came to the end of the Second World War, Japan was faced with a huge challenge: how to rebuild its economy within a relatively small country with limited space and financial resources compared to the US. And Toyota and other Japanese organisations were hugely influenced by some US guys, a guy called W. Edwards Deming and Joseph Juran, who brought from the US some radically different ideas for quality and how production should be organised that the Americans had pretty much rejected. Toyota and Ohno had also gone back to Ford, and they were hugely impressed with the scale and flow of the organisations compared to what they'd seen in the 30s, but also were hugely noticing the level of waste in terms of the large inventories of products that had resulted from the proliferation of different designs that I talked about a little while ago. Now, while they were in the US, they also went and saw these new things called supermarkets. And they were really looking at the way material flowed onto supermarket shelves compared to the sort of static nature of the Ford production lines. And he noticed just how well they managed the flow compared to those factories with the large batches. And he said there's got to be a better way to take some of this supermarket learning and set up a different way of offering choice to customers, where we had what we might now think of as the just-in-time or pull systems, which was tying all the factory production processes to ensure that supply of product flowed much more smoothly from suppliers into factories and through to customers. And as the Japanese became increasingly successful and made inroads of sales into the US and to Europe, Western companies really started to feel that pressure, as I mentioned, and were starting to research how that was done. There was a seminal publication, a book called The Machine That Changed the World by Dan Jones and James Womack and Daniel Roos, who'd led a research joint UK-US research project to understand how the Japanese did things differently. And it was around about this time that the term lean thinking or lean manufacturing was first coined to describe what Toyota and other Japanese companies were doing. It attracted worldwide publicity, and lots of Western companies started to attempt to copy what was happening. One of the interesting things was that Toyota wasn't really making any secrets of its system. It was very happy to share how it did what it did, and companies were eager to learn, although not all were as successful as Toyota by any means. And lean thinking over time has been applied progressively to increasing varieties of organisations. Just to underline that core idea of flow and moving things on one at a time, here's a simple illustration. On the left, we've got batch and queue production, where product is only moved on one batch at a time, which means that there's a lot of inventory accumulating between workstations. Compared to on the right, continuous flow processing, where product only moves on one at a time. This means that all the work done by the workers in that production flow is synchronized, and if we think about it, the time taken to get from the beginning to the end of the process for any individual part is significantly reduced because we don't have to wait for a full batch to be made. A lot of the practices of Toyota have been codified into what is generally referred to as the Toyota production system, which is really the origin of what a lot of people refer to as lean or lean manufacturing. And if we think about it in process terms, lean manufacturing is really designed to deliver both flexibility, efficiency and quality by focusing on those aspects of flow and pulling product only as it is needed through the system rather than pushing big batches. So one of the goals is to minimize inventory, ideally to work towards a batch size of 1 with processes physically linked together. By eliminating or minimizing the time to change between products, delivering quality through control of capable processes, not measurement of product, and understanding what all the elements of waste, time, energy, cost expended without actually increasing the value of the product. And so having defined it, there are processes in place to identify it and pursue its elimination by processes now referred to as Kaizen or continuous improvement. And underneath that, people started identifying processes such as A3 thinking, invented things called 8D, and from there we evolved Six Sigma, Lean Six Sigma, other approaches like theory of constraints, covering similar themes but perhaps with a slightly different focus, in that case eliminating bottlenecks. And a lot of the focus has been on these techniques, these methods for improving the flow of production. But if we study Toyota more, what we learn is that actually much more important is the culture of creating a workforce where the employees are all invested in solving problems and making improvements so that everything works better. You know, there's a famous phrase attributed to Toyota that goes, "First we make people who then make cars." If the late 80s and 1990s were characterized by an increasing focus on quality and also on optimizing production, so productivity, driving costs down, reducing time, the early years of the 21st century could perhaps be characterized as an increasing drive for more and more variety and individualization in products, increasing options and so on. To take one simple example, let's have a look at a product from my former industry. When the first Ford Escort was introduced in the 1960s, you could only have one wheel size, one wheel type, pressed steel, and 2 different tyre sizes depending on whether you picked the more or least powerful engine. By the time the 3rd generation Ford Focus came along, you could get 3 different wheel sizes, 15 different wheel types with various varieties and styles of alloy wheel, which needed between them 14 different tyre sizes. And that's just one example of one type. If we take that idea a bit further to see how the trend for variety and individualization has affected companies, let's look at my former employer and a product that's incredibly familiar to you, the Mini. By the time the first new Mini came along, we were already an incredibly long way from Henry Ford's one model and any colour you like as long as it's black. And yet, even less than 20 years ago, that first Mini was only offered in initially one body style, or 1.5 if you count the Cooper S with the scoop in the bonnet, and only became 2 with the introduction of the convertible by the end of its life. And of course each version was, like its BMW cousins, available with lots of options, but it was only those 2 or 3 basic varieties. By the time the 2nd generation came along, the number of body variants increased to 8, and with the 3rd generation, my Mini colleagues tell me that over the full life cycle of that vehicle range, there'll be 22 different vehicles, including BMW 1 and 2 series models built on the same basic structure. And if we then add all the increasing range of options that you start to offer in that search for individualization, that starts to present quite a challenge to both engineering and manufacturing. So if we take just one of those body types, the Mini Clubman, and we've got lots and lots of different options for colour, for trim, for country variant, for special deliveries, for seat type, for seat finish, for optional extras. I just wonder how many different variants of that Mini you think it would be possible to build without building 2 the same. In a face-to-face session, I'd normally stop people and get them to guess, but I just wonder what you think the answer is. You might be surprised to know that it's actually over 1 billion different types. And therefore we start to think about how we manage that complexity without having fields and fields and fields full of all the different parts, just in case we need them. So what of the future? What are some of the trends and developments that we see that are going to further affect the way in which products are designed and developed? One thing's clear, that despite a few temporary glitches, that trend for increasing individualization in products isn't going to stop anytime soon. Equally, the expectation that costs are going to be kept low is still there. And yet, with all the developments in technology, a lot of the drivers seem to be adding cost to product. So those two things in tension are going to place a huge number of challenges on the way engineers and manufacturing professionals work as we move along. If we take that idea to its extreme, we can imagine a future where every product becomes unique, produced to an individual customer specification, which requires an approach to thinking based on agile methodology. And at its simplest, agile could be considered as the application of lean in a high variety, fast response environment where people need things to happen quickly and in a unique way. And that requires a significant mental mindset shift away from the idea of how we design, develop product, test it and then put it into production. Because if we're only making one, then design becomes production. At one level, we're back to the days of craft manufacture, with the expectations around precision and cost and quality and reliability matching those of today's high volume, well proven products. Big shift in terms of our thinking. And we're starting to see the technologies to enable that evolve already. We know about 3D printing, and even on today's Mini you can have custom designed individual parts 3D printed for your car. Further in the future, people are talking about the idea of nano factories, building on the current ability of nano engineering, working at the molecular level. And we can see this sort of idea exemplified in what's happening in the pharmaceutical industry, where we're starting to think about drugs that are individually tailored to the genetic makeup of one individual, and therefore not requiring or being able to rely on the years and years of development and testing that we see with a lot of contemporary drugs. And the only way this is achieved is by really understanding the capability of our design and manufacturing processes, because there's no ability really to prototype, evolve and improve in the way we think about it today. Before we move on to some other design considerations that are going to be increasingly important as we move forward, let's just bring some of that together and look at where the different production approaches we've talked about fit in today's world by considering the impact of volume versus variety. So on this matrix, our horizontal axis represents variety. So low variety, one-off or same product variant on the left-hand side, high variety, lots of different variations on the right-hand side. And the vertical axis represents volume, low to high. So if we go back to our early days, right to the beginning of this session, and talk about craft manufacturing, we were on one-offs. So the ability of some craftsmen to take an individual customer's design and make it. And of course, back in those days, that was expensive and rare. As we moved through the Industrial Revolution, volume went up. We started to get into mass production. So mass production would sit in the low variety, high volume arena. So therefore cost starts to become more important. We don't need flexibility because all the product's the same. Actually putting parts into inventory isn't very high risk. It adds a bit of time, but it's not very high risk because we're producing lots and lots of the same product. If we move across to the right and we move into the era of mass customization, we start to bring in some of the ideas of agile, because to customers that cost and flexibility are very important. We start to get into the ability to change over from making one variant to another really quickly. Any inventory starts to become a risk because of the greater variety of product we're offering to the customer and the uncertainty as to what customers are going to pick at any one time. So that needs a lot of careful management. And if we come down to the bottom right hand side, we're into sort of the future world, or the high end of today's world, where we need an incredibly agile, responsive process to cope with rapidly changing customer demand, lots of variation, and a need for highly customizable products at low volume. And if we bring that all the way back to where we started, the expectation is people are going to want highly individualized, unique products, but at the same cost and quality and levels of performance and lead time that they've come to expect from today's high volume mass production world. So a lot of challenges and a lot of different approaches, and picking the right one for your particular organization and marketplace becomes increasingly important in terms of the design approach you might need to take to allow the production side to work well. And we can talk about that a little bit more when we get to our next face-to-face session. Looking forward, a lot of what we're seeing is just further evolution of the stuff we've already talked about. Even that agile thinking is actually just the evolution of the trends we've seen over the last couple of hundred years. However, there are a couple of other significant areas that we ought to consider. The first being Industry 4.0. You'll remember that I outlined the various elements of Industry 4.0 in the first video session and how they combine together to create lots of opportunities for creating innovative new products and services. These will have a significant impact not just on the products but on the design process itself. Working on these types of opportunities requires engineers from all disciplines to work more closely together, and we expect to see the boundaries between many of the traditional disciplines blur or disappear altogether as engineers from one discipline acquire knowledge, skill and experience in others. The other big change to think about is the idea of servitization, thinking about the customer requirement in terms of the service offered rather than the product. Examples of this are the automotive industry moving from selling cars to the concept of selling mobility, printer manufacturers moving from selling printers to selling ink and pretty much giving the printer away, to paper sheet models. And we'll explore this area a lot more in our next virtual classroom session. The other dimension is that the combination of the Internet of Things and big data analytics has opened up loads of new opportunities in this area of servitization. So things like preventative maintenance regimes driven by telemetrics, self-stocking cupboards and fridges, a whole wide range of servitized business models that wouldn't have been possible without some of those enabling technologies that have come across in the last few years. Another concept that's becoming increasingly significant is the idea of the circular economy, where we consider the full life cycle of a product, and in particular what happens to the product when it reaches the end of its initial working life. Traditionally, we would have given this relatively little thought, focusing more and more on reducing cost, throwing things away and buying new. In more recent years, the ideas of environment, material recycling and so on have come along. And organisations are now considering a much broader range of examples where products can be reused or converted into other products. The illustration on this slide is derived from the mobile phone industry, where whole new companies have grown up to provide second lives to phones or their components. In a similar way, batteries from electric vehicles are finding second uses for power storage or are being reprocessed to recover the raw materials. The more concern for the environment and use of scarce natural resources grows, the more significant these considerations will become, and design is going to need to consider more and more a whole system view of the product life cycle, as this diagram shows. There's clearly a lot to learn from history and some significant challenges as we look ahead to the future. And in the next few sessions, we're going to start to unpack some of the ways in which we can address those. In our next virtual classroom session, we'll build on some of the material that we've covered in the first couple of product lifecycle sessions and in today's video to think about how we design for all of those various considerations and how we organize ourselves to do that. We'll think about how the operating philosophy of your organization will impact the design process, how we accommodate all these different perspectives and identify what their particular requirements are. How do we accommodate all of the difference between those? So manufacture versus assembly versus service versus sourcing versus production versus after sales versus end of life versus anything else, and how we manage the trade-offs between those. What are some of the key principles that we can evolve that help us in that process? How do we evolve those into design guidelines, and then how do we put that into practice? What processes and disciplines do we need to enable that to happen? And to help you prepare for that next session, I've got a series of questions that I'd like you to ponder and bring back your answers to that next virtual classroom. So the first question I'd like you to think about is how you would characterize the operating philosophy of your organization. Things you might like to think about are: where does it sit on the volume variety matrix I introduced earlier? To what extent your organization is focused primarily on the product or more on the service that it's providing? Or you might want to pick up on some of the other ideas that we've covered. The second question, which might involve you going out and doing a little bit of research within your organisation, is to identify what are some of the challenges that your colleagues in manufacturing, supply chain, some of those other disciplines actually face with the design of your current product. What are some of the things that maybe frustrate them, make their life a bit difficult, add cost? What are some of the things that you can find out there? And the third question is to think about how your design approach impacts on the manufacturability and supply chain performance in your organisation, and perhaps how that might need to change in the light of what we've learned in this session and those that have gone before. The worksheet that you should have downloaded from the Learning Management System has got plenty of space for you to record your thinking on these three questions and bring them along to our next virtual classroom session. So, quite a bit to think about there. I look forward to hearing your conclusions and discussing them at our next virtual classroom session. Until then, goodbye and see you next time.